Here I will be discussing even more reactions of alkenes, and they are also unique in their own right. In fact, there are cases wherein these reactions can be discussed entirely in different chapters of some organic chemistry books, but the fact that they are all related somehow to how alkenes react will allow me to also discuss them in one entire go. They will include the 1,4 addition, the hydride and methide shifts, as well as oxidative cleavage. Let's start with 1,4 addition. In order for us to really grasp what this means, we have to remember first that if I have a compound with two double bonds arranged in an alternating fashion, that is double, single, and so on, we call these types of double bonds or systems as conjugated systems. And what's so special about this is the fact that since all of the carbons here are of sp2 hybridization, they would now have delocalization, meaning we can imagine the electrons moving constantly throughout all the atoms that are sp2 hybridized. Such that if we're going to imagine them going back and forth, it can be in this resonance structure, and on one hand, this resonance structure. Although we do know that in reality, none of these two are correct because the correct one is wherein all my pi electrons are scattered around the four atoms equally. But discussing it this way is gonna be confusing. But so I mean, in this case, we will use this and this instead. So let's use that exact same example. And let's say that I subject this alkene, this diene, into hydrohalogenation using HX. Now, we need arrows to really understand how things are going to happen. So let me start off by saying, first we must choose any of these two double bonds. Well, anyway, they are both equivalent. They are this alkene is symmetrical, and let's say I'm just gonna choose this double bond, and this will go to this H, being the electrophilic site, the electron poor site, and then this bond between HX will be received by the X given that it is more electronegative. And long story short, we will get this H and attach it to the alkene. Now, following the Markovnikov's rule, we usually put the H to the less stable carbon, or the carbon with more hydrogens, and between 1 and 2, with your basic knowledge of structures, you must already guess that I'm talking about carbon number 1, meaning we put our H here. And since in carbon 2 we don't have any electrons after the abstraction of the hydrogen, after the hydrogen has been bonded, this carbon will now become a carbocation. Okay. Now, normally, what we know is that once we have a carbocation, our remaining part that's negative, which is the X a while ago, will just conveniently attach to this carbon, and then our final product would look like this, wherein my hydrogen is at carbon 1, my X is at carbon 2, and we're done. And this is what we normally do in like so many reactions so far for alkenes. This is called the 1,2 product. Simply because if you look at the carbons that we attached our reagent with, or to, they are carbons, well, 1 and 2. And there's nothing surprising here. I mean, again, this has been what we've been doing for the last two videos on alkenes, and probably also for alkynes. But this is now what's interesting. The fact that I have a carbocation, and the fact that this is an sp2 hybridized carbon, allows us to imagine that this double bond right here between 3 and 4 could actually migrate to the bond between 2 and 3. If that happens, the double bond will now be between 2 and 3. And don't forget that we already have an H here at 1. The carbon 4 will now lack an electron, and therefore it may have the opportunity to become positive. And instead, there may be some situations wherein our X will target that carbon number 4. And if that will be the case, our product would now be different. Wherein my H now is, well, it's still at carbon number 1, nothing changed there. But the fact that now my X went to carbon number 4, this is now what we call the 1,4 addition. And if it weren't for the idea that we know resonance is going to happen, which will lead to this, which will lead to this, which will lead to this, then we won't understand. That's why it's essential for you to know what resonance was in the first place. Because if you do, then I think we don't have any objections as to the possibility of having a 1-4. Now, for simplicity of discussion, I will not discuss the factors that will favor whether 1-2 or 1-4 would be uh, more common. But usually in room temperature, 1-2 and 1-4 addition products are equally produced. Now, another thing that we need to talk about in terms of reactions of alkenes is the phenomenon that we call shifts. And they are 1-2 rearrangement reactions, meaning uh, just when you thought that reaction is over based on the usual reactions of alkenes, there's gonna be a rearrangement or switching of places, as I will show you later. First, before we even go to the reagents here with the color yellow, let's first analyze our starting materials. Let's start with this. So I do know that these are my two vinylic carbons, and I know that they are not equal. This is a primary vinylic carbon. This is a secondary vinylic carbon. And I know that based on the Markovnikov's rule, if I use this double bond to attach to my HX, this H will belong to the less stable one, which is the primary, right? So here, our primary carbon will get the H, meaning that the secondary carbon will be the one which will be a carbocation. Again, remember that this one is a secondary carbon. Now, I want you to look at the allylic carbon. Allylic meaning the carbon next to the vinylic carbon here. And if you are asked, what type of carbon is it? Well, the fact that I have three carbons here, this is a tertiary one. And, well, isn't it that tertiary carbons are more stable? What I'm trying to say here is that the fact that I have a carbocation, okay, besides something that is more stable, then we can imagine that this positive charge has the chance to go to this more stable carbon. But it cannot go here without a consequence. I mean, if you're gonna place this positive charge on this tertiary carbon, we must have something in exchange. Well, remember that since I have three bonds here, there is still one missing hydrogen. What I'm trying to say here is that maybe what we can do is we can, and let me find a different color for this. Maybe we can exchange the positive charge here for this hydrogen so that I would have a more stable carbocation. And well, that's what I was talking about a while ago, the so-called switching of places. Here, what happened is that we now switch the positive charge to give it to the more stable carbon. And in that case, my H moves to the other side. This is what we call a hydride shift because what we literally used to exchange the positive sign was a hydrogen. Oh, and by the way, don't forget that we already added an H at this carbon, which was originally this H from HX. So this is that H. And this H is the H that I used for the hydride shift. Okay, just to make sure we can track where we are. And of course, finally, the fact that my X is still missing, right? It's still yet to attach. Of course, this will now go to this carbocation. And, well, I don't have space, but you can just maybe we can just erase this. And then at the end of the day, this positive sign will go away and we will now put the X here. So this is what happens during a hydride shift. For example, let's have this one. Let's say I have this one and this alkene and I add HBr. So how do we usually respond to this? Well, normally what we do is we erase the double bond, right? And then I put my H somewhere and then I put my Br somewhere. Now, let's say that you put your H here and you put your Br here, which is better because what will happen is that if you realize that you placed Br at a secondary vinylic carbon, which is beside something which is tertiary, which of course you can imagine has a hiding hydrogen. Maybe this one and this one could switch by what I was saying a while ago, a hydride shift. And so if that happens, then that H will go here, the Br will go here. So actually, this is supposed to be the final product. So this is going to be, well, normally you don't need to write the H's when your structure is skeletal, right? So if I'm going to remove all the details, your final answer should look like this. So now, what could be a shortcut? Well, the fact that every time you see a tertiary allylic carbon, then expect a hydride shift. That's really the shortest way to think of it. Okay. Now, there's another type of shift which I will show you using this example. Before we proceed with the reaction, let's again assess the type of carbons that we have. So this vinylic carbon is primary. This one is secondary. Now, look at the allylic carbon. This is now a different type of carbon. It now has not just one, not just two, not just three, but four carbons around it. So this is actually what we call a quaternary carbon. And so let's follow the same dilemma a while ago, wherein, let's say I'm going to donate my double bond, give this to the H of OH, the OH will get the bond. So later, we're yet to see the OH attaching to the final product. So that would wait for later. And we remember that, again, since between these two vinylic carbons a while ago, this one is less stable, this would get the H, making this carbon a carbocation. Well, this is secondary, and again, the one beside it, the allylic one, is quaternary. This is not anymore the same as a while ago, because what we had a while ago is I have secondary beside tertiary. Here we have secondary beside quaternary. But the idea is actually the same. It's gonna be like, hey, I'm positive. Can you give me to the more stable carbon? And of course, just like a while ago, you can't do that for free. You're gonna have to exchange something for that. And well, unlike a while ago, this carbon doesn't have any H anymore, right? Well, what we can do is we can use a carbon for that uh, to take place. I mean the switching. So now, what will happen is that, so don't forget to write the H here that you added from the HOH. So it's like this, right? Currently it's like this. But then I mentioned that you're gonna switch one of the carbons and this positive charge. And so what it would look like after is something like this, wherein my positive charge is now on this carbon, and I did that with the help of donating, or let's say exchanging, one methyl group for it. And because what we used in exchange was a methyl group, we call this instead a Methide shift. And of course, it's not yet over, because this OH will have to go to this carbocation, and we can just imagine later on this carbocation will be gone, and it will be replaced by that OH. And therefore, this should be your final product. Hopefully, you already see the shortcut here, that all you need to see is a quaternary allylic carbon next to something less stable than it, usually a secondary or a primary. Usually it's a secondary vinylic carbon. And let's try to apply it to this example. So let's say I let it undergo hydration again, and of course, as always, in your product, the double bond will be gone, and you can imagine your H going here and OH going here. If you do that in this manner, then you would realize that, oh hey, my OH is in a secondary carbon, right? And beside it is, well, a quaternary one, right? And because you know very well that during the process here, you know that there's going to be a Methide shift, all you need to do is to imagine this, one of the methyls here, oh, I didn't erase, one of the methyls going out, because the OH going there, the OH is going there, and vice versa. So now the OH goes up, the methyl group goes down. And this should be your final product. So hopefully that gives you an idea how to use the shifts properly. The most challenging part really is in identifying whether there would be a shift or not. Add to that the fact that, well, based on their mechanism, the only reactions that can have shifts are hydration and hydrohalogenation, which exactly is the point why you're seeing my only examples in the slide are either HX or H2O. If it was another reaction of alkene, for some reason based on the mechanism, the shifts will not happen.